Hello, this lecture is going to be about more advanced patterns on the periodic table. You've already learned a few patterns like atomic number, atomic mass. You've learned about metals versus nonmetals. What other patterns have you learned? Valence electrons and electron shells. You may know some other patterns as well, but these are the big ones, and a lot of these we'll actually mention in this video. But today, more advanced patterns we're going to learn are actually something called electronegativity and atomic radius. And we'll define these terms first before we talk about how they're on the periodic table. But before we even do that, we're going to do some review on the electromagnetic force, because this is going to form the basis of how we understand this lesson. So there are two factors that affect the electromagnetic force. One is charge, so positive, negative, etc. And then one is the distance that the charges are away from each other. So more charge, I'll do just more charge, equals more force. And then what else do we know? We know opposites attract. And we know that like charges repel. So two positives, two negatives will repel. What do we know about distance? Well, we know that big distance equals less force. So the farther two magnets are away from each other, the less force they exert on each other. And then if they're stuck right next to each other, they're exerting a much bigger force. And then something that's going to be really important for today is that of these two, distance has a bigger impact. So everything else being the same, distance is going to affect the force more than charge will. Both will have an impact, but distance has a bigger impact. Okay, and I could do this the opposite too. Less distance equals more force. So the closer they are, the more force they feel. Okay, so that's going to become important. Let's learn about our two vocab terms. Atomic radius. If you know your geometry, atomic radius is actually pretty simple. So the definition right here just says the distance, so it's a length, from the nucleus. Nucleus, I remember, is the center of the atom. So the nucleus of an atom to its valence electrons, the atomic size. And I remember valence is the outer shell. Right? Because we've got multiple shells of electrons, at least most atoms do. And atomic radius, valence, would be the outer shell. So a small radius, I guess this would be the nucleus. And here would be the valence electrons. I'll just do VE. And then here we've probably got a nucleus. And we've probably got a lot more shells underneath here. But remember, this one is just the last shell. This is just the valence electron. And so the radius here is longer. This is a larger atom. We would say its atomic radius is larger. So that's the definition for atomic radius. What about this second word that we're supposed to be learning? Electronegativity. Well, I know electro makes me think of electron or electricity or a whole bunch of things actually. And then negativity sounds like negative. Well, I know that electrons are negative, so maybe there's a connection there. Let's read this definition. Ooh, it's a longer one. A measure of how strongly an atom attracts electrons. Semicolon. A higher electronegativity means that the atom attracts electrons more. A lower electronegativity means that atom attracts electrons less. So it sounds like this first definition, the key word here is strongly. So high electronegativity, I'll do En, equals strong at pulling electrons. Let's just do E minus. Let's look at this figure. So we've got H, we've got F. It says electron density distribution. And it says the figure above shows that fluorine pulls electrons more towards itself in a bond with hydrogen. So then if fluorine is pulling them more, that means fluorine is stronger. So this must have a high electronegativity, and hydrogen must have a lower electronegativity. Okay, so that's our definitions. Let's review them one more time. Atomic radius is the distance from the nucleus to the valence electrons. And electronegativity is how well an atom attracts electrons, or how strong it is, essentially. So let's look at this next figure, which in your packets I believe is on the next page. So what does this tell us? Atomic radius, so I know that means size, as a function of atomic number for atomic numbers 1 through 54. And remember, atomic number is the protons. Oh, didn't mean to move that. Okay, I think that's pretty much where it was before. So P plus, positive. Alright, what's it tell us to do? Circle the elements in group 1. What happens to the atomic radius as you go down the periodic table? Well, the elements in group 1, it starts with hydrogen, so there's one, and then we have lithium, which would be this one. And then the next one is sodium, which is right here. I'm already noticing a bit of a pattern, which is potassium's the next one, and I bet you can already guess. The next one is rubidium, and then after that is cesium, which, cesium's number 55, and this only does up to 54. So here's group 1. What happens to the atomic radius as you go down the periodic table? Well, the atomic radius increased as we went down the periodic table. Box the elements in period 2. What happens to the atomic radius as you go to the right across the periodic table? Okay, let's see. Period 2 starts with lithium, so it looks like we're starting right here, and then goes to beryllium, which is just the next one. Right, because it's organized by atomic number. So these are all of the ones, and it stops at neon, sure enough. Stops right there, and then it goes back up again to sodium. That's interesting. So what happens to the atomic radius as you go to the right across the periodic table? Well, the atomic radius, it looks like, is going down continually. So the atomic radius decreases as we go to, whoops, got ahead of myself, to the right on the periodic table. Interesting. Okay, and I was looking at a periodic table the whole time. Not a bad idea if you weren't following what I was doing. Oops. So to summarize, we have these two patterns actually. And this is the one we found with atomic radius, that atomic radius increases as we go down, and actually as we go to the left it increases, because when we went to the right it decreased, so the opposite obviously. So actually the lowest atomic radius is in the top right, and the highest, or the largest, atomic radius is in the bottom left. And then electronegativity actually has the opposite pattern. So high electronegativity is in the top right, and low electronegativity is in the bottom left. So there's two factors that control these patterns, and that's going to be protons and electron shells. So remember, protons have a positive charge, and opposites attract, so that means they will attract electrons. So if you attract electrons more and bring them in, you're going to have a smaller atom. Okay, what about electron shells? Well, if you have more electron shells, then electrons are farther from the nucleus. So this essentially is distance, and protons are affecting the charge. And we reviewed in the beginning of this video that distance is going to have a bigger impact, but both will have an impact. So let's look at periods versus groups. So why does atomic radius decrease and electronegativity increase to the right? So this is in a period. Now, something of note, in a period, what do we know? In a period, you have the same electron shell, right? In period 2, they all have 2 shells. So then these 2 factors, electron shells, are not going to impact our explanation for right here. So what's that leave us? Well, that leaves us protons. So how would we explain this? Well, more protons means the nucleus will attract electrons more. That's the electronegativity, pulling the electrons toward the nucleus, making the atomic radius smaller. Right? So do you get that? So if I have, let's say, lithium with its 3 protons, and its electron shells are, let's say, right here, and then I compare it to something in the same shell, not the same shell, the same period, like, say, boron, which has 5 protons, well, it's going to suck those electron shells in a lot closer because it has a lot more positive charge pulling those electrons in. So thus we have a larger electronegativity and a smaller atomic radius going to the right. The smaller atomic radius confuses people sometimes because you think, well, I'm adding more stuff, it should get smaller. Well, it doesn't, because you're actually attracting the electrons and it's getting tighter. So it's getting denser. More stuff, yes, but less volume too. What about going down? So going down, we have more protons, right? The atomic number is always increasing, but we also have more electron shells. And remember what we reviewed. If you have 2 of these, distance is going to have a bigger impact. And so actually, in this case, the electron shells are going to drive our explanation, right? So why does electronegativity increase and electronegativity decrease going down? Well, going down the periodic table, there are more electron shells, and so electrons are farther from the nucleus. That's atomic radius right there. And we can, since electrons are farther, the electromagnetic force attracting them is also weaker, decreasing the electronegativity. Because again, even though they have more protons, which you'd think would increase the force, those protons are so much farther from those electrons that these electron shells make them farther away and the force is lower. So let's see if we have time to do at least one sample problem. So which is larger and why? Silicon or argon? Well, first you got to find them on your periodic table. Silicon's right here, argon's right here. So in the same period, which means they have the same number of electron shells, and so what am I going to use to explain? Protons. So I'm going to say silicon has less protons and the same number of electron shells. Thus, the nucleus will attract electrons less, and the electrons will be farther away, increasing the atomic radius for silicon compared to argon. So silicon is larger, but again, you've got to use the vocabulary as always to explain it. So I'd be looking for protons, electron shells, attract, nucleus, electrons, and then of course atomic radius. Okay, we got like 30 seconds, then I run out of time. I can only do 15 minutes. Which attracts electrons better and why? Barium and magnesium. So barium is right here, and magnesium's right here. So these have different protons and different electron shells, but the electron shells are more important, and so we're going to use that in our explanation. So magnesium has less electron shells, and so the valence electrons are closer to the nucleus, allowing the nucleus to attract more. Okay, and I'm out of time.